to do is, again, we want to have our comparisons nested within our habitat. So we set this up the same way. We've got our slow-moving stream. This is microfar compared to water column, microfar compared to micronear, water column compared to micronear. Okay? So we set that up the same way. We highlight the same thing, and then we'll get this graph. Okay? But this is based off of the Sorensen's index instead of the Simpsons. Okay? And then, so you plot here the individual Sorensen's index for each of your comparisons. But then you'll see in number 9, it also wants to do, we also want to do habitat versus Sorensen's similarity index. So here, what we want to do is we actually want to take the average for all the comparisons and plot that. Okay? So when you're doing your comparisons here, you can take the average. Again, this is just equals average of this column highlighted. Okay? And then you can move these down here, copy these, do the copy paste special. And then we're just going to compare that to the average of the habitats, the slow-moving stream, fast-moving stream, and stagnant. Okay? And here, what we want to, basically here, what it's going to tell us is the number of species and where they're occurring, more or less. Okay. So our Sorensen's similarity index is showing us just how similar are these habitats and microhabitats. We can see here, at least in my made-up data, the stagnant pond has a higher similarity index. Which kind of makes sense, right? Because it's only one microhabitat. Okay? Any questions thus far?
What does the R graph tell us about 1 to 3 bars?
This one?
The one above this.
So this is just showing us the average of our Sorensen's index for each habitat. So we just took the average of our microhabitats and then put them together just to compare the different habitats as opposed to the different microhabitats.
But we didn't compare them to each other, we just took the average. Does this tell us how similar the...
Yeah, it's just, so this is just the average. So this, I mean, I see your point, but for whatever reason, that's the way this is.
Okay.
Because ideally what you would do, you would need this, so if you wanted to do this actually properly, you would take the comparison for the total for the habitat and compare each of the total habitat. Okay? Any questions? Alright. Okay, so now we're on to step 10. And here, what we're doing is our chi-square goodness of fit. So remember when we were talking about the Warren Woods data, I said that there was 2 chi-squares. One is the contingency table / test for heterogeneity, and one's the goodness of fit. So in the test for heterogeneity, we had no idea what our expected values were, right? And then in the goodness of fit, you can calculate your expected values and see how much it differs. So here, we're going to calculate our expected values and do comparisons for snails, damselfly larvae, dragonfly larvae, water pennies, and mayfly. Okay? So you just want to focus on those individuals, and that's why they're highlighted. So we want to total up the number of individuals across all 3 habitats. And in order to get our expected values, we total up the number of individuals of each species and then divide that by 3. Okay? So here, over here, are our expected values. And you can see that this is just the sum. Oops. So this is just the sum of this entire column. And then you divide that by 3. Okay?
Why are you dividing it by 3?
This is just how you get your expected value. There's probably a lot of other ways that you could actually calculate that. This is just kind of the throwaway way, the easiest way. We just say, add them all up, divided by 3. Okay? So all of your individuals divided by 3. That's the magic number for your expected value. Okay?
Why is it by 3 though? Because isn't slow moving and fast moving weighted more than the stagnant pond moving up 2 cents?
It should be, but not for this analysis. Because, I mean, so ideally what we would have done for the stagnant pond, we would have gone out there, we would have gotten the same calculations and whatnot. Don't worry about that. It should be weighted more. Don't worry about it. Okay? Just pretend. So then we have our entire row. We add it up, divided by 3. This is now our expected value for our water penny. We do the same thing for our damselfly larva, dragonfly larva, mayfly larva, and you should have snails somewhere. Do that for snails as well. So then we want to get our observed values, which are derived from taking total number of individuals across all 3 microhabitats within the habitat. Okay? So again, we separate our habitats back out. We've got our individuals per microhabitat. So for here, for water penny, for slow moving stream, we want to sum it for all of the individuals for that habitat, and we get 2. Okay, and it's the same type of equation, where it's just the sum of the row. And then you can pull that down for damselfly larva, dragonfly larva, mayfly larva, and also snails. So that's going to be our observed value for our slow-moving stream. Fast-moving stream is the same thing. We sum up all the number of individuals for the fast-moving stream, put that in there, put stagnant pond, and then you've got your expected values. Okay? So just like with Vassar stats, like we did for Warren Woods, we can go back into Vassar stats. There's a different place that you go to for this. So on your regular Vassar stats open, we went to clinical research calculators before, remember? You now want to go to frequency data. So you click frequency data instead, and then you'll get this page. So you scroll down on this page until you see the chi-square goodness of fit test, right? And this is the one you want. You don't want the contingency table, you don't want the test for heterogeneity, you want the goodness of fit. Go ahead, and I clicked on it, and then this is the page that you're going to have, okay? So now what you want to do is you're going to have to run a chi-square goodness of fit test for each of our individual species that we're looking at, so snails, damselflies, blah, blah, blah. So for each of our observed values, so each of our habitats, our habitat totals, we put in the observed frequency compared to the expected frequency, okay? So expected frequency is always going to be the same because that's based off of all of your habitats. And then the observed frequency is going to change based off of what you actually observed in your samples. Then you go ahead and hit calculate. And again, it's going to give you your chi-square value, your degrees of freedom, and your p-value. Okay? Here it says the test will have 2 degrees of freedom. So if you end up, when you put this in, you don't have 2 degrees of freedom, then you put your data incorrectly. So make sure you double check and kind of see. That's a good way to check it. And then a critical value is 5.99. That is just back when we made you do this all by hand. You would have a table that plotted like your possible critical values. You compare that to your degrees of freedom. And that's basically where you would get on this table what your p-value actually was. Since we don't make you do that, you already have your chi-square value, and it'll automatically give you your p-value. So is this significant or not significant? What's our, huh? Yes, it's significant. If it's less than 0.05, if your p level or p-value is less than 0.05, then that means it's significant, and then you can reject your null hypothesis, okay? So you can say that it is not, that there is no difference. So there is a difference. That make sense? Okay, so again, you have to do these for all